All right, what we're going to be talking about here is our finest little bit about acids and bases and our chemistry as it applies to this course, and that is the pH scale. So slightly more detail than we looked at in our discussion about acids and bases, but let's talk about this because it comes up quite a bit, and we can use this scale to determine things about acids and bases. All right, so the pH scale is a logarithmic scale, which means that every change of 1 unit on the scale represents about exactly a tenfold change on the concentration of the solution. So, for example, if the increase of 1 time on the scale would be a concentration by 10, or 10 to the 1, I guess, and a decrease represents by multiplying the of 2, sorry, by 2 represents by a 100. So that would be 10 times 10. Okay. So we just jump on that scale. Okay, so, right, so if my scale is 1, 2, 3, 4, from here to here is 10 factor, here to here is a 10 factor, and here to here is a 10 factor. So between this number and this number on the scale, this means that there is a 1 to 1,000-fold difference in the concentration between the things that we're talking about. All right, now the scale ranges from 0 to 14. Acids have pH values lower than 7. Okay. And then you have bases, pH values higher than 7. And then we have a special designation for exactly 7, which is something called neutral. So when we looked at our neutralization reactions, in essence, those reactions would result in a pH of 7 if you neutralized one with the other. Okay, whether the acid was neutralizing the base or the base was neutralizing the acid, they would neutralize together, and you would get this. So if you think back to those reactions, right, we have HCl plus NaOH, right, and then you form NaCl plus H2O. You could just think about the idea that this pH might be 1, this pH here might be 14, and when you get on the other side, you have pH 7. Okay. So even though the pHs weren't 7 originally, when you neutralize, you end up with pH 7. In theory, anyway. It all depends on the quantities of these in proportions, if you have the right proportions to exactly do this. Otherwise, you'd have some of these left over and it wouldn't be quite 7. But anyway. So that's why this is called neutral, and why we're talking about neutralizations, is when you take those lower pHs and higher pHs, they can cancel their pH and bring them to kind of an intermediary pH, like a 7. Okay. Oh, you can, I don't remember this. Car batteries, I think, are 2. I think drain cleaners are like a 13, something like that. You can always fact check me on that. Now this diagram down here is just showing it in a more pictorial representation. It's all giving you some images. There are colors here. In my copy, there isn't any. If you get it online from the posting, then you'll see the colors there. And the colors, we're going to actually use those in the lab. So not these particular ones, but there's going to be some colors associated with indicating what the pH is. But anyway, so here's neutral. So this was the neutral we talked about. This was exactly 7 here. Okay, and regular water, naturally occurring water generally would be, so if you just had waters, maybe not even like a pond or a lake, but if you just had water by itself, it's a pH of 7. Okay. Now, as the number gets higher, that's where you get more basic. So this says higher pH, more alkaline, or you can use basic. Okay, that's moving to the right. So moving from the left to the right. So moving to the right, you get more basic or more alkaline. As you move the other way, as your number gets lower than 7, you're becoming more acidic. Okay, and from moving from left to right to left. Okay. Now, what's interesting about this diagram here is some of these materials you probably have seen, like there's lemons and there's vinegar. This is vinegar. Tomatoes, bananas. I can't make this one out just from the image there, but you can eat all these, and so on. Okay, so they're not too dangerous for the most part. Depends on the concentration as well, because vinegar is not pure acetic acid. It's a solution, usually I think it's about a 5% solution of the acetic acid in the water. And these are probably low concentrations of the acids in here, but there is some. So generally, these things here that contain these acids in them, you can eat those. You wouldn't eat anything over here, uh, primarily just because they're cleaning agents, and I don't know, they don't taste. They're not nutritious. They don't look pure and living things. These are all commercial products to sell to clean things. Now this one's over here. So this we've used before. This is baking soda up here. Now what's interesting about the baking soda is that it's not an Arrhenius base. It doesn't actually have OHs in it. So this already tells you that we know that Arrhenius is not completely correct in his description of acids and bases, but he's pretty good. Okay? But this one, it would confuse Arrhenius because there's no hydroxide in baking soda, but it is still a base, okay? And so on. Okay? I think these are birds' eggs down here. All right. Now, as the pH decreases, so here's a decreasing pH, the solution becomes more acidic. The solution, a pH of 3, is 10 times more acidic than the solution of 4, right? So from here to here, this is 10 times more acidic than number 4. And 3 is also 2 steps away from 5, so it's 10 and 10, so it's 100 times more concentrated, and it's IH plus ions than number 5 is. And it's the same thing when you go the other way. As you go down, it's the same thing, a tenfold, 100-fold, 1,000-fold, 10,000-fold, and so on. So if you compare here to all the way up to here, it'd be like 1, 2, 3, 4, 5, and that would be what, 100,000-fold in concentration. Now, some AP content we're going to do with this is you can actually calculate some pH for this, but for you, it's going to be more problematic for us because you haven't covered one important thing in this course, which is moles. So I'm going to show this part as AP preparation. Now we're going to be talking about moles very shortly, but we are just going to assume, just imagine we know what a mole is. Briefly, a mole is really a quantity, which we'll talk about later. But you can actually calculate the pH if you know the amount of something in solution, or if you know the amount of something in solution, you could predict its pH from a calculation. So to calculate the pH of an aqueous solution, you need to know the concentration of hydrogen ions. So you need to know this. In moles. And it's supposed to be in per liter. And you'll see another word in there called molarity. So really all you need to know is how much moles are in my solution. Okay? And once you have that, that's a concentration. And then from this calculation, you can figure that out. And this is a logarithmic calculation because the scale is logarithmic. Okay? So this H plus represents concentration. So the actual brackets, if you ever see these used in chemistry, I think we used them when we talked about our gradients. This square brackets represent concentration. So if you looked at the equation up here, this is the concentration of H plus ions in the solution. All right, so if you had to use this formula just very quickly here, this is the amount of H plus ions I have. And we're only using strong acids and bases here. In this case, just acids. This calculation is not as useful for weak bases and acids because they don't dissociate completely, so they don't make ions from exactly what you started off with in that quantity. So the calculation is different. It's a more complicated calculation, but this will work for us for strong acids and bases. Okay. So the pH is this. So this is the amount of H plus ions, and I simply just plug that into my calculation. Minus log 0.0025. And you don't even have to have the unit there because it's going to punch out a number for us that will be effectively what we're going to use. Okay, so when you use this with your calculator, depending on your calculator, so this is where you have to kind of know how to use your calculator. Okay, so you're going to do 0.0025 and you log it. Okay, then you press log. You press log. And then the negative sign, then you just press your negative sign. It gets rid of it, and then you have the 2.6 pH. Okay. All right, so you can go the other way. So if you go from a concentration to a pH, use what is known as the anti-log. Okay. Now the anti-log is the same function on your calculator that is this, so 10 to the x. Okay. All right, so if you had a pH of something, what is the concentration of H plus ions? All right, so you do anti-log, you do minus, and then you're 8.34, and there, okay? So then you go back to your calculator, then you do your 8.34 negative, and you shift and then log, and that gives you 4.57 times 10 to the minus 9, and it would be molarity, which is moles per liter, which you don't know a lot about yet, so don't worry about that. You can just write a big M there, and this is my concentration of H plus ions.